Okay, let's unpack this. Today, we're diving into something really fundamental to how your phone talks to a cell tower. Channel State Information Reporting, CSI.
Right.
And the really exciting part, we're looking at how AI, artificial intelligence, and machine learning they're set to pretty dramatically change how this works, make it way more efficient.
That's absolutely right. Yeah, think of CSI reporting as this critical feedback loop. Your phone, the UE, user equipment, it's constantly checking out the radio channel between itself and the power, the base station.
Okay.
And then it needs to send a report back summarizing the channel's condition. Things like, signal strength, how the signal might be bouncing off buildings, that kind of stuff.
Right, so the tower isn't just shouting into the void.
Exactly.
It gets this, report card on the connection quality. And that lets it optimize how it sends data back to you, beamforming, that kind of thing.
Precisely. Directing the signal where it needs to go. But like you said, sending a full, super detailed description every single time, that would just eat up bandwidth.
Way too much data. So it's already compressed, this report.
It's already compressed, yes. It's a summary. And the source material we're digging into today, it's from Roden Schwartz, some transcript excerpts about their early research. It's all about using AI and ML to make that compression even smarter, even tighter.
Okay, so our mission for this deep dive then, understand this AML compression idea, look at the clever testing setups they had to use, because this isn't standard yet.
Not at all.
And figure out what the key finding is, what makes this so promising for wireless efficiency down the line.
Let's jump right into that core concept then. So we know CSI reporting compresses info, like about beamformers, how to shape the signal. The AML idea here involves training a neural network.
Okay.
One on the phone side acts as a super efficient compressor. Takes all that channel data, boils it down into a really small bunch of bits.
And this is the bit I found really interesting. It's not just the phone using AI.
No, that's key.
They also need a matching AI decompressor, another neural network running on the base station side.
Correct.
To understand that super compressed report and rebuild the beamformer info.
Yeah.
So AI is potentially deep in the network infrastructure too.
Exactly. It's a two-sided AI system, which is, pretty advanced stuff for this stage.
Right.
And because it's so new, it's not in the 5G standards yet. You can't buy a phone that does this.
Which is why they needed the special test gear.
Precisely. You have to simulate this future tech to even see if it works, how well it works.
So let's talk about that testing setup.
Yeah.
How did Roden Schwartz actually go about it? What gear did they use to sort of stand in for the base station and this future AI phone?
Okay, so the main piece was their R&S CMX500. It's a one-box signaling tester, very versatile.
Yeah.
And in this setup, they configured it to act like the base station. So it's receiving the signals, processing them, doing what a real tower would do.
Okay, CMX500 is the tower. Got it. And on the other side, they needed something playing the role of that hypothetical AI phone.
Yeah, the one generating the AI compressed report.
Since you can't just grab one off the shelf.
Nope. They had to simulate it. And they talked about two main ways they did that.
Okay, what was the first one?
The first used a software-based approach.
A software phone. How does that work exactly?
Well, they used something like MATLAB to build what they called a software-defined UE. This software was set up to do the standard CSI stuff, figure out the channel, prepare a report structure the base station expects. And here's the clever bit. Instead of using the normal 5G rules for the compression part...
They swapped in the AI.
Exactly. It fed the channel data into their neural network encoder. And the output of that AI encoder, that compressed bit string, is what it would then transmit.
So it uses the normal pathway, the uplink channel, to send the bits.
Right.
But the meaning of those bits, and maybe even how many there are, is totally different. Defined by the AI. They called this minimally invasive, I remember.
Yeah, that was the term. The idea was, can we slot this AI compressed data into the existing signal structure without totally redesigning the whole phone-to-tower communication?
So the tower just needs to know, this report is AI compressed, use the special decoder.
Pretty much. Switch to AI decoder mode for this one.
What kind of AI were they using? Did they mention the network type?
They did. It was based on a structure called IMCSINet. Essentially, it takes that channel description, that snapshot of the radio path, runs it through these layers designed to find the important patterns, and then quantizes it, boils it down into that compact bit string.
Got it. So MATLAB UE figures out the channel, AI encoder compresses it to bits, sends it to the CMX500 tower.
And the CMX500, which is also running the matching AI decoder they developed.
Right.
takes those bits and tries to reconstruct the original channel details, or specifically the beamformer directions.
And how did they test if it was actually better?
They simulated a realistic scenario. A phone dropped randomly in a city environment, with signals bouncing around, fading.
Standard urban clutter.
Right. And the key was they could capture and replay the exact same channel conditions over and over.
Ah, so you could do a fair comparison. Apples to apples.
Exactly. Compare the AI method directly against the current standard methods under the same condition.
Okay, and what was the big result from this software approach? What did that comparison actually show?
This was really the core finding they wanted to highlight. They showed a graph essentially plotting reconstruction quality against the number of bits used in the CSI report.
Fewer bits is better. Quality needs to be high.
Right. And the AI-based compression, they showed it as a blue line, it consistently needed significantly fewer bits to get the same or sometimes even better reconstruction quality compared to the standard baseline method, which was 3 GPP Tech 2.
Wow. Okay, so less data overhead for the same result.
Or even a better result in some cases. It was, as they put it, mostly superior, even though the report size was much smaller. That's the efficiency gain you're looking for.
That definitely sounds promising. But, a software simulation, it's great, but it's not quite real radio waves flying through the air.
True.
They also used a hardware approach, too, didn't they, to get closer to reality?
They did, yeah. As a sort of complementary method, they swapped out the MATLAB software UE for a piece of hardware, a dedicated signal generator, their R&S SMW200.
Okay, so now we have actual test equipment generating the phone's signal. How did the SMW200 handle the AI compression part?
So the SMW200, its job is to create real 5G uplink signals, the kind of phone sends. For this test, they configured it to generate a special kind of data packet on the main uplink data channel, the PUSCH.
Special how? What was in it?
Well, it contained the AI-compressed CSI report, just like the software version did.
Okay.
But crucially, it also included extra debugging information alongside it.
Ah, stuff for the engineers running the test.
Exactly. Info that a normal phone wouldn't send as part of its CSI report, which is why they mentioned this specific transmission wasn't strictly spec compliant for CSI.
Right, it wasn't pretending perfectly, but it was sending the important AI data plus that extra debug info.
Correct. The debug info was vital for them to analyze what was happening.
And the CMX500 was still playing the tower role.
Yes, absolutely. CMX500 still acting as the base station emulator, listening for and processing these unique uplink packets coming from the SMW200.
How do they manage all this? Telling the CMX500 which AI model to use, telling the SMW200 what special packet to build.
They used scripting, basically programming the test setup. They could specify, CMX500 load this neural network decoder file, and they could define the exact structure of that custom uplink packet for the SMW200 in a text file where the AI bits go, where the debug info goes, all configured through the software controlling the instruments.
And how did they verify the results in this hardware test? Was it just watching signals?
They looked at detailed message logs generated by the CMX500 after the test scenario ran.
Logs, right.
These logs would show things like the configuration, confirming the right AI decoder was loaded, and crucially, they'd show the output of that decoder.
So what it made of the AI bits it received.
Exactly. How it reconstructed the channel info, or the beamformers, based on the SMW200's transmission. That allowed them to evaluate the AI's performance in a much more realistic radio frequency environment.
Okay, so putting these two approaches together, the flexible software sim and the more realistic hardware generation, it really shows Roden Schwartz has the capability, the tools, to dig into these really cutting-edge AI applications right in their lab.
Precisely. It demonstrates they can test these complex future ideas like embedding neural networks into core 5G functions using their existing platforms. They don't have to wait years for standards and commercial chips.
They can test it now.
They can test it now, investigate it, see the potential.
And both methods, ultimately, they were validating that same core finding from the simulation, right? That efficiency gain.
Absolutely. That was the goal. Both the software and hardware setups were ways to explore and confirm that key finding. Using AML for CSI compression looks like it can offer really significant efficiency improvements.
Adding fewer bits.
Drastically fewer bits, potentially, to send that vital channel information while keeping the quality high, maybe even improving it compared to today's methods.
Okay, so let's bring this back. What does this actually mean for you, the person listening? Why should you care if AI compresses CSI bits better?
Well, it matters because, as we said, CSI is fundamental. It underpins efficient data transfer. If your phone can send its report using far less data,
Right.
that frees up valuable space on the uplink, the channel from you to the tower.
Less congestion, maybe.
Less congestion, potentially less interference, maybe faster responses for things you do online that need quick feedback. It allows the network to potentially support more users more effectively, handle more complex services in the future. It's like, making the communication highway wider and smoother.
A foundational improvement. Okay, so let's quickly recap then. We've looked at this early research, like the work from Roden Schwartz, exploring AI and ML, to seriously shrink that CSI report your phone sends up, using specialized test gear like the CMX500 and ways to simulate or generate signals from future AI phones.
Like the MATLAB approach or the SMW200?
Right. They've already shown really promising results. Fewer bits needing to be transmitted for the same, or maybe even better, quality of channel understanding.
And it really highlights how important these kinds of flexible test environments are. They let engineers really push the boundaries, test integrating things like neural networks into the nuts and bolts of communication, way before it's all standardized and in everyone's pocket.
Proving the concept, gathering the data.
Exactly. That data is crucial for potentially feeding into future standards, like maybe 6G or later 5G releases.
So this early work on AI for CSI shows some real efficiency wins are possible. Which leaves us with a final thought, something for you to maybe mull over. If AI and ML can bring this kind of significant optimization to something as fundamental, as data-heavy as CSI reporting, what other really critical, complex processes inside our cellular networks might be next?
Interesting question.
Things like how the network schedules data for different users, or manages handovers as you move between cell towers, or even just optimizes power consumption. Could AI bring similar efficiency boosts there? And, maybe more importantly, how soon might those kinds of behind-the-scenes AI improvements start to subtly but noticeably improve the mobile experience that you rely on every single day?
This video content source from the R&S YouTube video titled AI ML-based CSI Feedback Enhancements with the R&S CMX500 one-box signaling tester. Thank you for watching. See you in the next video. Bye.